In this example problem, we'll be looking at finding the forces on three books, each of which are stacked one on top of each other on top of a table. So to visualize what this looks like, I'll draw it out. So we'll have our table. We'll have three books sort of forming a pyramid. For simplicity, I'm going to call these A, B, and C. Their masses are increasingly light as you go up. The mass of A on the top is half a kilogram. The mass of B is 1 kilogram. And the mass of C is 2 kilograms. Now I want to find the forces on all three objects. The weight is going to be an important part of finding these forces. The weight is going to be m times g, where g is the gravitational field. Now g is 9.8 meters per second squared, but for the purpose of this problem, I'm going to round that to 10 meters per second squared. Not because it's more accurate, but because it makes the numbers a little bit more round and you can see the pattern a little bit better. In fact, with this, we won't really even need to use a calculator to find all of these forces. So we have our three objects, excuse me, A, B, and C, and I'm going to do free body diagrams for them. So I take my whole objects A, B, and C, and I'm going to shrink them down to a dot, and I'll show all the forces on them as arrows on that dot. Now, the easiest object to start with will be object A, because object A has the least number of forces on it. Remember, the way that we're going to tell which forces are on an object is to first ask, is there gravity? Do they have weight? And the answer is yes, if they have a non-negligible amount of mass. So the masses, since I listed them, should not be negligible. Reason why they are heavy at all, if they're kind of being squished, is because of their own weight. So this, physically, you should intuit that gravity is important here. Otherwise, they could just like float at that spot. And then the next thing you ask is what's touching it. So there's only one thing touching book A, which is book B. We're neglecting any force from the air in this case. We'll get into forces from the air that aren't drag, on wind. Somebody's not going and blowing them down type of thing. We'll get into that much later. So for now, we'll neglect that. It won't change the answer, by the way. Okay. So for object A, we'll start there. A is only touched by B, whereas B and C are touched by the thing that is both below and above them. Object A has its own weight, so I'm going to draw a downwards arrow for that force. I'll use capital F for always for all forces. The type is gravity, so I'm going to use a subscript G. The object is going to be by the Earth. I'll use E for the Earth on A, because the Earth is the thing that pulls you down. Gravity is the how it pulls you down. And then you're going to have an upward force, because the book B is going to push directly up on book A. So we have a normal force, that sort of contact between the two surfaces, a normal force, and it's by B on A. Now, you don't know how these relate to each other in general unless you know something about their acceleration. Newton's second law will tell us about the combined effect of all forces, the net force, and it says that the net force on A is the mass of A times acceleration of A. Now, these are just stacked on a table, sitting in a room. The velocities aren't changing, so therefore, their acceleration is 0. And therefore, the net force is 0. So the net force on A is 0. The net force on B is 0. And the net force on C is 0. In a following problem, a follow-up problem, we'll look at the case where the acceleration isn't 0 and look at what happens to the forces. Okay, so in this case, we have the gravitational force. Its magnitude is ma, the mass of A, times g. The mass of A is half a kilogram. When you multiply that by 10 meters per second squared, that gives you 0.5 times 10 is 5 newtons. Since the upward force must cancel the downward force, the 5 newtons, the top force must also be 5 newtons large. Okay, that's all the forces on A, because the only thing it's touching and included gravity. Let's move on to B. I'm not going to do these to scale, by the way. I'm going to try to. I'm not good enough to draw them exactly to scale. So I have the weight of B, because I can ask, does it have weight? And the answer is yes. I'm going to say this is by Earth on B. I'm going to try to make a large arrow, if it will let me. I also have a force downwards and a force upwards due to the things that it's touching. So I have a normal force from each of the things it's in contact with. C will push up on B, C on B, and then A will push down on B because it's touching it. And so I have A on B. And now I can go through and find them. Its weight is mg, that's mb times g. So that's 1 kilogram times 10 meters per second squared, which gives me 10 newtons in that case. The size of A on B is equal and opposite to B on A, because remember, by the third law, the normal force by A on B is equal in magnitude to the normal force by B on A. Now, it's an equality because I have no vectors, and that means I'm just asking about the magnitude. If I had vectors and I include, therefore, the direction, I would have a negative sign in there. So if it's 5 newtons up here, then it has to be 5 newtons down over there. So you have a 5 Newton force and a 10 Newton force downward. They sum up to 0 when you add a certain force upwards. To cancel out a 5 and a 10, you must have a 15 Newton force upwards. Now I'm going to go through and I'll find there are again 2 forces downwards. The gravitational force by the Earth on C, which is mc times g, the mass of C. That's 2 kilograms times 10 meters per second squared. So that's 20 newtons downward. I have the force, the normal force. B is pushing down on it, so by B on C. Again, that's the same size of by C on B, so that's also 15 newtons. And then I have an upwards force due to the table. By table on C, if I have 20 newtons down and 15 newtons down, and they're canceled out by this force to give me 0, then it has to be 35 newtons upwards in sum of those two. So these are all the individual forces. I show you the direction of all of them, I give you the magnitude of all of them, and this applies only if there's no acceleration. We'll talk in a second about what happens if there is acceleration.